In this example, we've got an arm which is rotating in a horizontal plane. We know that at this instant, the arm is rotating with a constant rate of 5 radians per second. There's a cord which is attached to particle P, and someone is pulling in that cord at a constant rate of zero point 0.5 feet per second. Two things we want to know. One is what tension do we need in the cord to bring in particle P at that rate? And two, what's the contact force between P and the slot in this arm? So let's look at our FBD. FBD of particle P. It's in a horizontal plane, so we don't have to worry about weight. So the forces that we have acting here, we have a normal force here, which I'll talk about that in just a bit. We have a tension force like this, and that looks like it. So we have a tension force T, a normal force here. It's in a horizontal plane, so we don't have to worry about weight. And therefore, when we use our Newton equations, we're going to want to be able to resolve our forces in a way that it makes sense. So what I'm going to do here is define a polar description. ER is pointing outward from O. O is here, so it points outward from there. I don't really need an angle here, but I'm going to draw one in and say, well, that defines what I'm going to use for my unit vector of E theta. The point being is I'm going to use polar unit vectors for resolution of the forces and therefore for my kinematics. So as I sum my forces in the radial direction, I have this tension force, which I have right here. That's going to be in the minus E sub r, and that's equal to mass times the radial component of acceleration. I'm going to sum forces in the theta direction, and that gives me N, and that's equal to M times A theta. One thing I might say here before we get too far into our calculations is that by me drawing in like this, I could have drawn it on the other side, but my assumption here is that it's in contact with the surface here at B. If I would have assumed it was in contact surface for A, I would have drawn in the other way, down and to the right rather than up and to the left. Our math will tell us whether that assumption was correct or not. So for kinematics, what's A sub r? Well, A sub r is r double dot minus r theta dot squared, so that's r omega squared. It says that the rate at which that's being pulled in is a constant. So we have that. And then A theta is equal to r theta double dot plus 2 r dot theta dot, like that. It also says that omega is a constant, so theta double dot is a 0. So when we solve for this, we see that T is equal to minus M A sub r, so that's minus r omega squared. So mr squared, that's good, it's plus. It means that we can do this by pulling on the rope. It would be difficult if it weren't. We'd have to be able to push on it with a rope. N in this case is equal to m a theta, so that's m times 2 r dot omega. Okay, so what do I have? Maybe put some numbers in. Let's see what we get here. Tension force T is equal to the mass of this thing, which is 5 divided by 32.17 to get that in terms of mass. The radial distance r is equal to 0.75. Omega, the rotation rate, is 5, so that's a 5 squared. So that would tell us the tension force there of T. N. N is 2 times mass, which is 5 divided by 32.17. R dot, here is where we have to be careful on the sign. It says it's being pulled in, so R dot is a negative, and it's being pulled in at a rate of 0.5 feet per second. So this is a minus 0.5. Omega is 5. So what number that we have here is going to be a negative sign because of that. So what does that mean? Well, it means that my assumption was not correct. I assumed it was in contact with B. That's wrong. So therefore it's in contact with surface A. And we see here what dictates that. If we were letting out the cord, if there was enough rotation here to be able to for that enough rotation, if the tension force were small enough, the particle would move out rather than in. In that case, if R dot were plus, that would change the sign of this. It would change the sign of that. So whether we're pulling it in or whether we're letting it out dictates whether it's in contact with side A or with contact with side B. How we found this out, we just made an assumption and then we let the math give us the answer.